Welcome everybody. Welcome. First thing that I would like to say is 300. We have a Sparta complete. We have 300 members in our group, which is amazing. It is, it is hard to imagine that there's there we go. That there are so many people actually coming in and working in this industry that want to go and join our group. I thought it was quite a big milestone. During the presentation, it would be good to mute your microphone. Some people have mechanical keyboards. It's very nice, but makes it very hard to hear people. If you have a question, toss it into the chat during the presentation. When the presentation is done, I will scroll through the chat and then we can have some questions and answers. And this part is actually being recorded. So let's get started. First thing I would like to say is that we have an awesome Discord community. There's the URL here if you want to join it. We have some great discussions there. And we have lots of things that are not hacking related that we also talk about. So if you're interested into being more involved in our community, feel free to do so. There's already, I must say, an older version of this slide deck available on our companion website. We have a companion website called HackTheBox.nl, which is also the name of our Discord server. You can find a blog post which has everything on it. Let's see. Oh, Hidde just mentioned that the invite doesn't work because I guess the URL changed. But Hidde will put one in the chat, I would think.
There's a new one in chat.
Yeah, it changes every once in a while. I put it to not expire, but apparently it failed. Technology fails me. But anyway, slides will be are currently available. So if you want to download them and just scan through them, they're a little bit outdated because as somebody who was going to do a presentation in the evening, I spent most of the day during my breaks to just work on it. So it's a little bit different already, but most of the general parts are there. So in case you're just wanting to screen it. The video, as I already said, we will make a Vimeo channel and put video on and then post it on the website as well, and probably also in our Discord. So if you want to view it back later, you can. What to expect today? As I said, we are going to have a presentation, which will take about an hour, I guess. And afterwards, we'll have the two things that we can do, the reverse engineering workshop. Most people already chose to do that. If you don't want to do it, you can just hack on the dedicated lab. We have that to our use. We have it until after the meetup, which will be ending at 9. And then we have to pass it back to HackTheBox. But for now, you can just enjoy the silence on a dedicated server. And then we're going to talk about just enough reverse engineering to score some challenge points. Reverse engineering is a very wide and very interesting topic, which will take, well, about, I guess, a couple of weeks to actually fully explain. And then we have just one part of it explained. So my challenge for today that I set myself is to give you enough information to actually get started on HackTheBox. Who am I? My name is Arjen. On HackTheBox and Discord, I go by CredMP, which is a typo from the late 1990s. So if you can figure out what it is, drop me a line. What do I do normally? I work for Nova University of Applied Science. I head up the cybersecurity faculty there. And this meetup is part of my program to actually connect with the community. And besides that, I'm a certified malware reverse engineering instructor for Kaspersky. Kaspersky is not very popular now in the Netherlands, but it used to be. And they have a malware reverse engineering course, which is really nice. So I got certified into giving that. And part of the techniques that we use for malware reverse engineering actually work generally for reverse engineering in general. So that's my creds. Let's see. The goal for today is to introduce you to the field of reverse engineering. What is it? What can you do? And how do you generally go about it? I'm going to show you several tools that will form the basis of your reverse engineering toolkit. So these are things that you can just always use and do some reverse engineering. And we'll talk about some tricks that capture the flag challenge makers use to make a challenge more challenging. So let's see. What is reverse engineering? It's the very basic question as to what is this thing that we are actually trying to do. Reverse engineering is actually defined as the process of extracting knowledge or design information from anything man-made. So most of us in some way have always been doing reverse engineering. If you ever ask the question, how would that work? And you try to figure it out, then you've been doing some reverse engineering. And it's the very cool thing that you see with kids. If you have children, you will notice that if you give them something which is somewhat complex, they will try to figure out how it works. And they look at it from all these angles and they try to moving it and they take it apart. And somewhere down the line, we get conditions that we need to let stuff be, but actually taking time to figure out how stuff works is actually the process of reverse engineering. And what we're talking about today is actually reverse engineering when it comes to computer systems or software products. And if you look at it from a computer perspective, reverse engineering actually gives you a much greater understanding of how computer systems work. If you can figure out why that program does the thing that it does and how that works, you become bigger than that program and you learn so much more about why it is like the way it is and how you could actually circumvent it or make use of it in other creative form. It is great fun if you like puzzles, and luckily we're part of a HackTheBox community, which is basically all these people that like puzzles and trying to figure out how machines work and spend endless amount of hours on services that crash all the time. If you don't like puzzles, the entire reverse engineering thing is not a very good choice because it will take a lot of time. And a very nice thing, it allows you to peek under the hood of any product. If you go and you buy a webcam that you have connected to the internet somewhere, then it is quite interesting to see if you can figure out how it collects data, where that data goes, and how that gets dispersed, and if you can change it in any way that it actually does the thing that you want it to do. And that is quite fun to do. There's this guy, I have some Reolink cameras, and there's this guy that got really annoyed that it does not allow to do real-time stream processing for the video. And so he actually reverse engineered the camera, then reverse engineered the protocol, then wrote a thing that actually does the RTSP, and then rebundled that firmware and uploaded it to the camera so it would do the thing that he wanted to do. That is an extreme example, but it is a very interesting example because that is the entire thing about reverse engineering. If you like to get into that community, the Reddit reverse engineering community is awesome and shares a lot of information like that. So with a basic understanding at what reverse engineering is, and we're doing this on computer systems, then it's quite interesting to know how are these computer systems created. The first thing that we actually need to talk about is why we would do this with the context of HackTheBox though. HackTheBox next to the machines has these concepts of challenges. Each category has 10 challenges, and reversing is one of the challenges. So there's 10 binaries that we can look at from different degrees. There's one insane one currently called poly, which only has like the outer right red marker to say it's an insane thing. But most of the challenges are quite doable, especially if you have a little bit of knowledge as to how to get started. And today you will then learn enough to actually do the easy challenges and to get started on the harder ones. So what are binaries? What are these things that we actually want to examine? And to get a clearer understanding is to actually take a step back and to look at how these binaries are created. It sounds really simple, but it's a complex process. It generally begins with, or generally it always begins. There is somebody with a lot of feedback. Let's take a look. Can we mute everybody? Mute all. There we go. Mute all. There we go. So binaries are begin with somebody writing some source code. We write source code in a language, and if you write it in an interpreted language like Python or Perl or something like that, you never compile it. But any other language like C, C++, Rust, Golang, those are languages that we actually compile into something else. They get compiled generally into an intermediate language called assembly, which is the language to actually talk to machines. Compilers do this internally, but if you would write a compiler, your first step would be to read source code, transform it into assembly, and then assemble that into an object file. And the object file is the machine code representation of that source file. You then take library files, because you never only write your own code. You use code from other things like system libraries or cryptographic libraries provided by somebody else. And these things get linked into a binary file. And that can be done in various ways. We'll talk about that later. But this binary file is basically the product that we, in the end, get. But a binary file can be used for something which is very, very obvious, is that an operating system can actually start up or load a binary file. And then that binary file becomes a process. It actually consumes memory and uses CPU cycles, and it does things. And if you only look at your computer now and you look at the things that are running, you see a lot of processes, and most processes will have a binary file which was used to load it. But it does not mean that a process always has a binary file. It could be a result of some other thing that happens that generated a process that does something. And if we then look at reverse engineering, where does reverse engineering fit in? What is the thing that we want to be doing? We have this binary file, this thing, this artifact that we download and do stuff. And we can load this binary file into a process and just have something running in memory and using CPU. And these are actually two distinct areas. The first area of that one binary file, it's called static analysis. It is not running the software, but actually looking at the software and trying to figure out what it does without running it. And then when we run it, load it into the computer system, it becomes dynamic analysis. We look at something that is running, that's actually doing things, which is interacting with machines and maybe internet, stuff like that. Generally, when you're in the field of malware, it is very unwise to just run stuff. You first need to figure out what it does. In the field of capture the flag challenges such as HackTheBox, you are safe to assume that it is not a harmful thing that is going on. So dynamic analysis would just be running the binary to figure out what it will ask for you. But these two fields have different approaches. And we'll first start with static analysis. Static analysis is a very awesome thing to do. You look at something which starts out as a black box, and by using several tools, you can figure out quite quickly what the general purpose of this tool is, or this binary. The first thing you do if you look at HackTheBox, I took the example of the baby RE, which is one of the challenges. First thing you always want to do is to compare that you have the right thing. If you have the right binary from HackTheBox downloaded, if it is there correctly. If you download a sample from the internet, it will always have some form of checksum, either MD5 or SHA-256. HackTheBox now uses SHA-256, and so you can use SHA-256 sum to actually compare that your download is actually successful and downloads the right thing. And then you want to extract it. Most people get stuck here already because the default extracting a zip file, you would use unzip, and unzip does not allow you to actually fill in your the password for the file, and will say, yeah, I failed. And then they stop. We actually have to use 7zip to extract the archive. But once you do it, it will just provide you with a binary on your file. Every package that you download from HackTheBox will have a password. The password is HackTheBox, which is not very secret, of course. But if you don't read the instructions, you might want to figure out that there's a password and that you need to know it. So we have this binary now, and what can we do then? First step that you want to do is to figure out what you're actually looking at. You might know the command file, which you use to figure out if what type of picture it is, or what type of archive you're looking at. A file basically determines the file type. It will tell you what type of file you're looking at. But when you run it against a binary, it shows you so much more. And this is quite interesting because it will tell you what type of executable you're looking at. On Linux, we want to have an executable of type ELF. On Windows, we actually are looking for a portable execution format, which you might know as an EXE. On Mac, we have different formats. Maybe on embedded devices, there is its own type of format. So a file will already show you this. There's actually a screenshot below, which for baby, which says, hey, this is an ELF binary. It will then also tell you the type of architecture. If you want to run something, you need to know what the architecture is. In this case, it's an x86-64 binary, which means a 64-bit binary on the x86 instruction set. The x86 instruction set is basically the thing that allows us to see what type of machine instructions are used. Goes a little bit far to explain it here, but generally, if you run a normal system for HackTheBox, you will have an x86 processor on which you can run 32-bit and 64-bit programs. Most of the simple challenges on HackTheBox will have this x86-64 ELF binary format, and we can run it on our HackTheBox virtual machine. The endianness, which basically means do numbers get stored from left to right or right to left, is also indicated, but it's not called endianness in the output. It's called LSB, the least significant bit indicator, which means the least significant bit first, which means that it's a little endianness. We get to use that at the moment that you actually want to interact with your binary, and you need to mess with memory addresses, and then you need to know the sequence into which you need to put all the addresses. For the simple challenges, it's not really necessary, but it's a good thing to know about. And the last thing is it will tell us if it's a statically or dynamically linked binary. And now we are talking about static analysis and dynamic analysis now, and now suddenly we're talking about static and dynamic linking. Linking is that last step in the process of getting a binary, and it is something completely different from an analysis point of view to a linking point of view. But what it means to have statically linked binaries means that your binary will have all the code from the object file and the library file inside that one binary. And so it's very portable. It does not depend on outside libraries. It has everything inside that one binary file. Which also means that all the functions used by your binary, all the code needed to do that, is part of that one file. So there will be a lot of functions generally in order to support basic operations like string comparison, interacting with your terminal, stuff like that. On the other hand, dynamic linking, which the sample here is, actually relies on a shared library being available on the machine that you're trying to run it on. And so in this case, it will say that it's lib64 ld linux x86 blah blah .so.2 and that it's meant to run on a GNU Linux 3.2 machine or higher. Dynamic linking means that your binary will be a lot smaller because it does only contain the code that you wrote in your source file and does not contain the code that actually came in through the libraries. But it does mean that if you don't have the same libraries available that the application actually needs, then it will never run. You need to then provide all those libraries. And so you might need to build an entire system just to provide the libraries just to run a sample, which can be quite a headache. From a reverse engineering perspective, it is easier to reverse engineer something which is dynamically linked, simply because the amount of code that you're actually looking at is a lot smaller, and there's no pitfalls into jumping into code that actually came from a library and stuff like that. So it's a good thing to keep in mind. If you ever run into problems and it's a dynamically linked thing and it does not want to start, you need to figure out what library it is actually missing, and you need to take steps to actually install those libraries. Next step that we can do is we can run something called strings. And strings is a very simple tool, very simple in its working. It will actually read every byte of a binary and determine, oh, is this something that a human could read? So like A through Z and all the special characters. And if it's a readable character, it will look if it is followed by readable characters, and if it is, it will create a string, and it will print that string onto the screen. So you get everything that is readable by a human in a binary onto the screen. So the description is list printable strings in a binary. It is a very complex thing to actually do right. But when you use strings, you get a lot of information. You can determine the function of a program. If we look at the screenshot, there is a strings on the headache example. Headache is one of the more complex ones, so there's no spoilers here. The only spoiler here is that it will already show some functionality. One thing that jumps out is the part that says initializing enter key, login failed, login success. So from there, you can already determine that there is actually a requirement for you to add a key to the executable, or when you run it to enter a key. So there's probably a key that we need to figure out and that we need to reverse in order to get our flag. Sometimes people like to taunt people looking at binaries. In this case as well, some challenges you can just run strings, and it will provide you with the answer. In this case, if you look at the second to last line in the printout, it says HTB curly brace not so easy lol curly brace close. That is the format of a flag. And so they're actually taunting us to say, well, nice try, but this is not how easy it is going to be. I actually am still currently working on Headache, and it is quite a headache. It's quite interesting. One thing to know is that every file in some way will always have a sequence of printable characters that get bashed together and then look like a string. Generally, they're like 4 or 5 characters long, but strings will print those for you. So if you have a large binary, you will get a lot of output. In the case of this screenshot, I have limited to say, give me only strings of 10 positions and higher, because there was just so much output. If you look at some of the steganography challenges, there will be hints or challenges inside pictures, and you can use strings to actually get information from a picture that is actually hidden inside, which is quite useful. Another thing that strings will tell you is the functions that are actually used during the running of this application. One thing that that is quite viewable in this screenshot is that there's a libc start main function, and there's this itm deregister tm clone table and register tm clone table. Those might give you clues as to what actually happens inside a binary. But one thing that can happen is that strings only gives you garbage, and that can certainly happen. And one of the challenges that we'll look at in a reverse engineering workshop, if we get that far, has this problem. It's called packing. Packing is a trick people use to basically obfuscate their binary. So you don't want to have tools or people looking at the contents of your binary. You can pack it, and you can see this as a Matryoshka doll, where there's a doll inside another doll. So we run a binary, and that binary opens up, it starts writing its program code into memory. And then the first thing it does, it opens up and puts out this other doll, loads this one doll into memory, and then says, well, now you get to do the thing. Basically, that's the process of packing. And the tool that is used most of the time for this is called UPX, which is the ultimate packer for executables. And it's quite something to say that you're the ultimate one. There's actually many different tools that do some packing, and it's quite easy to write your own packing. Basically, what you do is you grab your binary, you put that in some format, sometimes you compress it, and then you write a program that gets that chunk of compressed data, decompresses it, loads it into memory, and then you hand off execution to the point where you actually loaded your stuff. But UPX, it hides your binary in other binaries. It is only loaded at runtime. So if you look at it from a static point of view, you will never figure out what it's supposed to do, unless you know about packing and actually say, well, I want to investigate this system. And then you can use UPX-L, and then it will list the packed executables in that file, and that you see in this screenshot as well. It says, well, this executable of 220 or 220 kilobytes will actually become 709 kilobytes. There's I've blotted out the executable that it involves, but running UPX, you can decompress it, and then it basically will write out the original binary, and then you can start your process anew. You run file to determine what it is. You run strings to see what it actually does, and you step into the next process. The next process is actually to look at what the thing does. We only looked at what type of file is it. We looked at what is in it that I can read. And then it is the step to actually move that binary back into its chain that we saw earlier and move it into the assembly phase of its existence. You can do this with pretty much anything that runs on a system. And there's basically three tools. You see 4 icons, but there's actually 3 tools. One is Ghidra, one is Radaro 2, which has a separate interface called Cutter, which is the logo beneath. And on the right-hand side, we have IDA, IDA Lovelace, but IDA is a commercial tool. Actually, today they actually launched a new version of IDA and IDA Home, which can be yours, IDA Home, for just €1 per day, so 365 euros per year. And if you want the full commercial one, you have to add some zeros to that. But it is a commercial tool by Hexrace, but it's loved in the industry. It was the original disassembly tool that actually makes working with binaries very pleasant. The commercial one and also the freeware one come with a debugger. The big difference between the commercial one and the free one that we can all use, it is limited in size, and the free one does not have a decompiler. If you remember from one of the first slides, it went from source code to assembly to object file to binary. We are now working backwards. We are working from a binary to assembly, and we actually want to go all the way back to source to actually make our life a lot easier. With IDA, you can go to the assembly stage and you can have a really good tool to actually look at assembly and work with assembly. It just does not have this decompiler that we would make our lives a lot easier. The entire scene for disassemblers changed 2 years ago, I guess, when Ghidra was announced. Ghidra is a product developed by the NSA. And the NSA, like most of us know, are very interested into breaking into computers. And so they have this really cool workflow for examining software. Yeah, you can think a lot about this, but basically every state nation actually does this. And the NSA actually open sourced their tool. It has been open sourced. The funny thing about Ghidra at that time, it was announced, it was released, and you could download it. And people in the reverse engineering community and in the malware reverse engineering community said, well, I don't trust this tool. It's made by the NSA. It probably is bugged and this and that, which is quite ironic if you're in malware reverse engineering. So you should know how to deal with that. It's quite interesting discussions. Ghidra, it is not the most intuitive tool, but it is very powerful. You can extend it, you can add scripts to it. And the most important thing is that it comes with a decompiler. And decompiler takes that step from assembly back to readable source code. Up to this point, people not in the industry, not with a commercial IDA license, had to rely on reading assembly and understanding assembly, which is quite a task. We now have the ability to take that next step and look at decompiled code. It is not perfect. It will not compile into the same thing that it decompiled, but it will give you enough readable syntax to actually understand what is going on. If it says, well, I'm doing a string comparison of two strings, you can figure out what it actually does. And most challenges, especially the easy reverse engineering challenges that we're going to look at in workshop, are very solvable by just looking at the tool through Ghidra and looking at the reverse engineered code. Sad thing for Ghidra is that there's no debugger yet. They've been promising that they are working on a debugger for the last year. I think they already have a debugger, but they have not added the code to the open source project yet. But that would make it next level, that we can actually step through debugging into decompiled code, which would make it like you're actually working on a software project that you actually wrote yourself, but very badly because it tries to figure out complex things. But Ghidra, it has become one of my favorite tools. There's also Radara 2, which describes itself as a libre and portable reverse engineering framework. It is so much more than just disassembly and working with binaries. It has things that you can actually script using some bash scripting tools together to actually do stuff with binaries. The original Radara 2 was a console-based application, and there was a web-based thing which did not really work. Somebody actually went to the effort to create an interface on it called Cutter, which is becoming quite good. It is so much more than just a disassembler, but the Cutter GUI, so this GUI product on top of Radara, now also integrates the Ghidra decompiler. So they took the code from Ghidra, which was open source, and they added it to Cutter in order to decompile the binary and look at the functions inside it. So you can get the same output from Ghidra in Cutter. So basically both are quite interesting to look at. And the really cool thing since last month, I guess, is that it now has an experimental, or beta as they call it, debugger. So it is becoming a full-fledged tool to actually step through code and look at systems. But if you remember, static analysis looking at binaries which are at rest. Dynamic analysis talks about running stuff. And if you talk about debugging, it is actually dynamic analysis. So for now, my advice, and we'll do this in the reverse engineering workshop after this, is to just get started with Ghidra. We'll download it and we'll set it up and we'll start with it. And we do this because it is the least hassle to actually get started. And then once you have done several challenges, we'll take a look, or you'll take a look at IDA and Cutter, and then you can make your own mind up as how would I have solved this challenge in this tool or in this tool. It gives great perspective to compare tools from a standpoint that you actually look at the same challenge and how would I go about to actually do this. And then if you want to go a little bit further with reverse engineering, I would say pick one tool and learn it really well. Learn the workflow and get used to it, because most of the time it is just a matter of being comfortable with your tool, and that makes the difference between being able to solve a challenge or being frustrated and not just getting it. So for now, my advice, use Ghidra. But I was already talking about dynamic analysis. A debugger is basically running the software. So you make the switch between static analysis to dynamic analysis. And dynamic analysis is quite interesting. We have some really cool tools to work with it. The first simple step that we can do is called tracing. Linux allows you to actually hook into the execution and instrument applications. And the first tool that we can use for that is ltrace. It is not on Kali by default. You need to apt install it. But what ltrace does, it says it traces library calls performed by the binary. So if you remember, when you compile a source file, you assemble it, it becomes an object file, and this object file is linked to library files, and together they form this binary. The most common library would be to have a C library, which forms the basic functionality of a operating system, opening files, doing random number generators, putting stuff on the screen, getting stuff from a user, comparing strings, stuff like that. Most challenges will get you to actually input something, and then if you input the right thing, you get a flag. So if you can just look at a binary, run it, and see what it is actually trying to compare, then there's no need to actually do a lot of research. You can just find the value that it's trying to compare against, and then you can solve a challenge. The second tracing tool that is available is called strace, where L stands for library, S stands for system. So the S will trace system calls and signals performed by the binary. So it will tell you about how memory management is done, file operations, the more low-level system call type things. But these two tools give a lot of information, but not every binary will allow you to trace into a system. As a developer, I can make certain functionality that will actually break the functionality of the tracing software. So if I want to make a challenge more difficult, I will make it so that you are not allowed to actually trace into the application, which is a dead giveaway that there is more to find in this application, of course. And the next thing, the most useful thing is using a debugger. With a debugger, you can actually step through a program. You can take one step after another and just get a little bit of information each step of the way. You can also manipulate the program. So if there's a comparison that returns false, but it will only continue the right path when it's true, you can actually manipulate the application while it's running through the debugger and set a flag from false to true, and then the computer will do the thing that it actually did not meant to do, but you convinced it to do it. So that makes a debugger a very powerful thing. You can manipulate what the application does, and then you can figure out how can I actually tweak this application to do this thing that I want to do. And very interesting, once a program loads, you can also examine the memory of that application. So if there's some obfuscated text segment, which you found using strings, and you look at the binary in a static way, and you can't figure out how that piece of text is actually used in your application, you can by using a debugger, you can see what it actually does, and you can take that piece of memory and then manipulate it in various ways. These are more advanced topics, of course. It makes you need to have a good understanding of how the application is run, how memory is used. So most of the easy challenge and moderate challenge does not require you to do anything of this sort, but it is quite good to know. There's several options. IDA or Cutter will do a debugger. It will allow you to step through the code, but you can also use a dedicated debugger, which is basically the thing that I actually end up doing most of the time anyways. You can use GDB, which is the OG debugger under Linux. I learned that OG actually means original gangster, and that has been, according to the Urban Dictionary, shortened to the original debugger for Linux. It is a very powerful thing, GDB. It has been around longer than I've been on this earth, I think, but it is quite extensible. The screenshot that you see here is actually Jeff, for which there's a link right here, which allows, which is actually a collection of just bash scripts that do stuff in GDB, and it manipulates the GDB interface to do all these wonderful things of showing the stack, showing the arguments, and disassembling the code each time you take a step. But it can be quite troublesome because it is extremely powerful. Does also mean that it is very hard to learn. If you want to actually deep dive into a binary and manipulate the way it does things, you need to type in all these commands that you need to have this booklet next to your keyboard to actually figure out what you want to do once you get into the more complex areas. But if you want to take the time, it is very powerful. And if you learn it really well, you are unstoppable, for sure. An alternative to this application is Evan's debugger. Evan thought it was quite hard as well. And he made a graphical based debugger, more a GUI. It is modeled on Ollie Debug, which is a debugger for Windows. It looks quite Spartan, but it has all the things that you need in order to examine an application. But as you can see, it will show the assembly code, and it will show the registers, it will show the memory, and you as a reverse engineer need to figure out how that stuff works. Generally, it is a great alternative for GDB for most cases. If you want to have something much more powerful, if you're at that point, you might as well learn how to do that thing in GDB anyways. Yeah, so these are the tools that we actually need. We have some tools for static analysis. We have some tools for dynamic analysis. Dynamic analysis, just running the application, seeing what it does. At this point, we don't need to worry about network traffic, stuff like that, because we're focused on capture the flag binaries. If you want to do malware and stuff like that, we have to talk about environments and capturing network traffic, stuff like that. But when talking about capture the flag stuff, there's this thing that we really need to understand, because capture the flag people, or actually the makers of capture the flag things, love XORing stuff. XOR is an exclusive OR, and most of the time, except for the really easy ones, I find CTF developers will XOR at least once a flag or the thing that you need to figure out how it works. It will have some form of binary operation like XOR in it. XOR is basically an operation on the binary level. It will take a look at the value, the binary value of the thing that you give it, and then perform an operation on it. I have an example that we can just talk through it. But whenever it compares a binary value, it has this simple rule: output true, so a 1, only when the values differ. And with that simple rule, it allows you to do something that most people, when they first see it, think like, what the crap is just happened? Yeah, and it's one of the binary operations that gets used most. And luckily, it is easily implemented in any programming language. So if you know some Python or you know some Golang, the carrot will do it for you. But let's take a look at one small example, and then you might get a good idea of what it does. I have this small binary fragment, 0011, which is the decimal value for 3. 3 represented in binary, but if we want to XOR that, we need a different value. We need 2 values. So if we take the value 0101, which is the decimal value of 5, so we're XORing 3 with 5. The simple rule, we can just talk from left to right, and if we look at the digits and we apply this rule, we'll get the value 0110. So if we look at the first digit, at both numbers, it will be a 0. So does it differ? No, so it returns a 0. The second digit, the first one is 0, the next one is a 1. Does it differ? Yes, so it outputs a 1. Next one, a 1 and a 0. It outputs a 1 again because they're different. And the next one, 2 ones. Are they different? No, so it will return a 0. And now this purple thing actually is the decimal value of 6. So 3 XORed by 5 becomes 6. And so when you get across this and you think, oh, okay, how would that work? If we just apply the same logic again, so we now take the 6 and we XOR it by 5, so the same thing that happened with the 3, look at what happens. The result will be 0, 0, 1, 1. Because the first 0, both are 0. Do they differ? No, so it becomes a 0. Then the 1 is in both numbers. So do they differ? No, so it becomes a 0. Then the 1 and the 0, do they differ? Yes. So we have a 1, then a 0, so they're different. So we need 2 ones. So we have a 1. Next one, the 0 and the 1. Do they differ? Yes, they differ. So it becomes a 1. And we're back to the original value. We're back at 3. So 3 XORed by 5 becomes 6. And if we have 6 and we XOR it by 5, it becomes 3. And this is used in so many things in these challenges. So it's good to understand, but much more important it is to understand that if you see a XOR, you need to think about the caret sign in Python, and then you just put the thing that is being stored into a Python interpreter, you XOR it, and then you see the actual value. But from a challenge point of view, if you know this, you can solve pretty much most of the challenges. Wrapping up, let's take a look. Where can we go with all this information that I gave you? Well, we can do the reverse engineering challenges on HackTheBox. We'll do that in a workshop. If you're interested and want to dive deeper into reverse engineering, you will eventually need to learn assembly. And there's a website, beginners.ray. He has compiled a sizable book now, in which he compiles some C code and then looks at assembly and compares what is happening, so you can figure out what instructions lead to what assembly operations. And that is really interesting. If you want to continue learning reverse engineering and taking the first steps after this 1 hour introduction and then a workshop, I can highly recommend Malware Unicorn. Amanda Russo, she's quite awesome. She has several workshops that she's been doing and that she's providing for free. Reverse Engineering 101 and 102, so still starter level, but very interesting. I would say an icon in our industry, and so very good to look at. And if I get you somewhat excited into reverse engineering, there's actually more challenges to be done, somewhat advanced and very interesting to do. In this fall, I hope we will have another one. Is the Flare On competition, where FireEye actually has a 12-week program in which they release challenges, and we get to do some reverse engineering, and that goes from Windows to some very insane graphic manipulation thing and just figuring out how stuff works. And if you're really bored, you might want to go to crackmes.cf, and there's thousands of crackme challenges that you can do, so you can spend eternity working on challenges. By now, you now know how to perform some basic static analysis. So we have the sum checking, we have file, we have strings, we have UPX, and my advice is to use Ghidra. So we can do some basic static analysis. Then we get started with dynamic analysis. We have ltrace, we have strace, and I would suggest running EDB as a debugger in case you want to debug something. And you now know how exclusive OR works, which is a life goal on its own, of course. It's very useful to know when working with these challenges. So there's nothing actually stopping you from getting some points tonight. I think most of you will solve at least 2 or 3 challenges tonight. I hope. So that's it. That's it for my presentation. My goal was to keep it within 1 hour. I actually did that. So I don't see the chat here, so I'll stop presenting and we'll take a look if there's any questions.